Hello, everyone. My name is Mikhail Shalaginov. On behalf of our research team, I would like to present our latest results on Metasurface-enabled wide-angle stereoscopic imaging. What I see recently is that the digital world is rapidly expanding into the real world. And for merging the two worlds, for example, in the case of AR/VR, one needs to know precisely what and where the real objects are located. And vice versa, if we are augmenting the digital things, we need to generate them of adequate scale and in the specified location. Similar tasks in 3D imaging and sensing are pursued in other application areas, such as self-driving cars, robotic navigation, and human-AI interaction. If we look into the optical engines enabling these technologies, we will see that they're primarily based on conventional optical components, such as refractive lens. And those traditional components possess inherent limitations in field of view, resolution, complexity, and form factor. However, there is an appealing approach for building superior lenses, also known as metasurfaces. Metasurfaces are planar periodic arrays of sub-wavelength elements, antennas. What are the key benefits? The sub-wavelength nature of meta-atoms opens up additional degrees of freedom to manipulate electromagnetic fields. For instance, arbitrarily sculpture the optical wavefront. Then, these structures are optically thin, lightweight, offering a significantly smaller form factor. Additionally, depending on the choice of materials and fabrication methods, the metasurfaces can be mass-produced in existing semiconductor foundries. In 3D imaging and sensing, there has been already several demonstrations leveraging metasurfaces. Some of them were inspired by insects. For example, in this case, by the spider catching the flies. The metasurface acts as a spider eye. It produces two defocused images of the flies at two separate areas of an imager. Then, after involving image processing, one can figure out what's the distance between these two flies. Yet another demonstration is the micro-metalens arrays enabling a light field imaging, which can form a set of images with a distinct depth characteristics. Another interesting application is to use the metalens chromaticity. Then the RGB color channels will form images with sharp features at different depths. Or, for example, we can also engineer a point spread function, which would have depth-dependent intensity profile. All of these are really cool demonstrations. However, from my point of view, they're quite far away from immediate practical applications. And here, what I'm showing today, our team is going along the path of traditional methods of 3D sensing, which is based on the stereoscopic method, and we utilize our previously developed fisheye metalens. Back in 2020, we released a paper where we experimentally demonstrated a single-element fisheye metalens made of lead telluride on calcium fluoride and operating in mid-infrared. On the left side, you can see its schematic. Essentially, it's a flat, monolithic 2 millimeter thick substrate. On the front side, there is an aperture opening. The beams go through the aperture, refract, spread out in the substrate, and at the bottom, they interact with a judiciously designed metasurface. That metasurface at the bottom focuses the incident beam onto a flat image plane. The SEM of that metalens is shown on the right, surrounded by the experimentally recorded focal spots, which are diffraction limited over the entire field of view exceeding 170 degrees. Actually, this fisheye metalens is already rivaling the existing refractive fisheye components. Here I'm listing the key features of our fisheye metalens. In addition to nearly hemispherical field of view and diffraction limited resolution, this metalens is significantly more compact and lightweight. I would like to emphasize that being compact is not the only advantage, since the optical metrics are interrelated with each other. Generally speaking, the fisheye metalens paradigm gives optical engineers extended parameter space to build superior optical engines. I already mentioned earlier, they can be streamlined into the existing foundries. As a result, massive production will potentially reduce the cost. Another important aspect that this architecture is wavelength agnostic, so it can be applied to a wide range of wavelengths, from visible to mid-infrared. And there is a trade-off typical for metasurfaces, bandwidth versus efficiency. Here we optimized our metalens on efficiency, so it does operate in a narrow wavelength band. The group of Carl Renshaw performed a more rigorous comparison of existing wide-angle lenses. On this graph, the x-axis is the field of view in steradians. The lenses with hemispherical field of view are on the right side. The y-axis is the volumetric channel density, or VCD, which is basically the lens resolution normalized to its volume. For instance, while it can make a high-performance refractive lens, but inevitably its volume will be large, since such lens requires about a dozen of stacked optical components. Conventional off-the-shelf refractive fisheye lenses are outlined with a black ellipse. In contrast, our fisheye metal lenses, primarily due to their significantly reduced form factor, demonstrate volumetric channel density 10 to 100 times larger than conventional optics. We adopted this architecture for constructing fisheye metal lens in the visible range at a wavelength 670 nanometer. For the materials, we used amorphous silicon and fused silica, which are standard CMOS foundry materials. Circular aperture defined on the front is 1 millimeter wide. The backside metasurface is 8 millimeter in diameter and contains about 500 million of meta-atoms, which were fabricated by electron beam lithography, followed by reactive ion etching. Now, if we zoom into the bottom side metasurface, you will see a 2D array of cylindrical nanopillars with a diameter varying from 110 to 170 nanometers to cover the full 2-pi phase delay range. Here is a photograph of the fabricated 1/2-inch fisheye metal lens. We have carried out its optical performance characterization, and here you can see the profiles of the recorded focal spots corresponding to specific angles of incidence. The PSFs are nearly diffraction limited. In our design, we targeted the full width have maximum of 2 microns in order to match it with the size of a standard imager. For implementing a stereoscopic imaging setup, we have used this 4K off-the-shelf CMOS imager with a nominal pixel size of 1.67 micron. Here you can see the two photographs demonstrating the whole optical setup. The middle photo shows the backside view, two imagers mounted to the translation stages, and then also the two objects used for 3D imaging. So these are the orange sweet pie pumpkin and gray gerandal pumpkin sitting on the chessboard. Now the right image depicts the same setup, but now from the front. So these are the two fisheye metal lenses nested in aluminum holder. Here you can see the raw panoramic images taken by the two juxtaposed fisheye meta cameras. Yellow dashed line outlines the circular image boundary. As expected, the images exhibit a barrel type distortion, which is typical for any fisheye lens. Now, if I zoom in, this tiny green pitch of the right image, we'll observe a high quality resolution down to pixel size. By performing image analysis, which involves a bunch of things such as camera calibration, image rectification, disparity map generation, and its inversion, so we can retrieve the depth map from the previously shown panoramic images. So this is shown on the left side. It's not ideal, but it captures well the spatial location of the two pumpkins. From this demo, our metalens-based setup allows depth sensing in the distance range of few centimeters up to a meter. So here are the take-home messages. First, we implemented a fisheye metal lens in the visible. It has hemispherical field of view, nearly diffraction limited point split function. It's a few millimeter thick and made of CMOS compatible materials, silicon and silicon. And second, by utilizing our fisheye metal lenses, we constructed a stereoscopic 3D imaging module with an ultra-wide field of view, pixel limit resolution, and depth imaging range from a centimeter to a meter. The last thing I want to say here that During the last decade, metasurfaces have significantly matured and are no longer only toys of scientists. Now they're emerging, their product deployment stage, and soon will be routinely used in our everyday life.